Hello and welcome to Verbose Mode by TuxCare at Dev to Next in sunny. You can see the sunny right here, and beautiful Colorado Springs in Colorado. And my first guest is Pranay. Welcome, Pranay.
Thank you.
And you all see the first episode of the TuxCare Verbose Mode that is streamed everywhere. We will switch to YouTube only after that. So all the next episodes follow TuxCare on YouTube to not miss them. But let's talk with Pranay about a very, very fascinating topic: cognitive load in code. Mm-hmm. What does it mean? I mean, software is complicated.
Right.
Can we say anything better than that?
So, my background is in system integration and consulting. I work with large organizations, and a lot of my work is around modernizing existing code. And one of the challenges that we face is we encounter a lot of complexity in code that is often unnecessary. And we've been struggling with this a lot, and I have very smart engineers on my team that often I see are struggling to understand the code, and I often wondered, why is that? And then when I did some research, I found out that there is actually something called cognitive load theory that explains the limitations of how our brain functions, and which explains why my engineers have faced this challenge. And that led me to look into a little bit more about cognitive load theory and make the connection with software engineering. And that is the inspiration behind this talk, because there are ways in which we can avoid that complexity without compromising the quality of the code, and in the long term, not just benefit ourselves, but the folks who are going to come after us and maintain our code.
So I don't think anyone wants to add complexity and increase cognitive load on purpose, right? It's not something that people, let me build the most complicated system in the world, right? This whole complexity is a sort of a technical debt.
Correct. And there is often the complexity is accidental, it is not intentional. It is introduced by not understanding the patterns correctly, or maybe overusing patterns that may not apply to the problem at hand, right? So often we hear of this term over-engineering, and that is often the reason why this complexity creeps in. But sometimes it is intentional, right? Some engineers, they are looking to make sure that their architects are impressed by their work, and they feel like they need to use the most complicated pattern in order to make their work look serious. And that often introduces that complexity and therefore the cognitive load.
Yeah, no, you have a point. I wonder, I guess there are two questions there. The first is, how can we measure that? And the second is, how can we improve?
Yes, so in terms of measuring, there are tools available out there, right? So, and especially with AI being an inherent part of development these days, I feel like that is one of the best uses of these AI assistants, where they can help analyze the code, and before you even try to, rack your brains around trying to understand the code that you're looking at, you can ask AI, your favorite AI assistant, to analyze the code and tell you something about it.
I love it. So it's basically write your code as simple so even AI can understand it.
Correct. And also, even before
it's a problem because the models progress. And maybe, Claude 4.5 was released yesterday.
Yes.
Maybe it will understand more complex code.
Correct.
So people will try less hard to optimize it, because now the models are getting smarter.
Exactly. So where I'm coming from, where legacy modernization is kind of the mainstay of my work, I feel like, to me, that is an apt use case for these AI assistants to understand existing code, to kind of break down and distill the complexity that lives in them. But even before these AI tools, we had static analysis tools like SonarQube, PMD. We've had these all along. And I think using them to prevent that complexity from coming in the first place, that is one thing. And if it has come into, like in my job, I often come across code that I had no control over when it was written. But then I can use these tools to analyze the code, understand the complexity, and then figure out ways to resolve that without boiling the ocean or disrupting or introducing bugs, right? So that is where I think the tooling is very much relevant, and it is improving and getting better in measuring the complexity, understanding where it lies and how to address it.
That makes sense. And then I guess you have some measurable, tangible numbers
Correct.
that you can refer to while you are going to optimize.
Correct.
So how do you put a number on a complexity?
So it's kind of, it's hard to, there are certain ways, like for example, if you, there's a measure called cyclomatic complexity, right? So how many linear paths you have in your code. So your tools can measure that. You can set your own standards around how large a particular method or function body needs to be, right? So you can create a rating scale where you can say, if I'm finding n number of instances of functions that are a certain size, then the complexity is large, medium, complex. So just like we do in Agile, where we do t-shirt sizing for our stories, I think that is one good way of measuring complexity, because complexity, like everything, is contextual, right? And when I talk in my talk, I'll talk about things like essential complexity, right? There are certain problems that are inherently complex, and you can't make them simpler. Einstein once said, "Make things simple as possible, but not simpler." Right? Because there are certain problems. If you're writing a cryptographic algorithm, there is only so much simplicity that you can add to it, and at some point it will be complex. But there are these extraneous complexity things which we introduce ourselves, which doesn't have to be there, but we still introduce it either accidentally or intentionally. That's the complexity that I think we need to go after and measure. So depending on the domain and the problem space you're in, you have to be contextual about how you're measuring the complexity.
That makes sense. That makes sense. And then getting back to the cognitive load. Do you use the cognitive load argument as a way to highlight the existence of the problem, or are there also users in solving it, in detecting it, in like any other, except of just saying, hey, if you feel overwhelmed, that's because your code is too complex, and then let's put aside this argument and work on the complexity?
That's it. So it's two-pronged, right? So prevention and cure, right? It's both, right? Prevention is always better than cure. So obviously, introducing this concept early on, and like I said, intelligent people, smart people struggling with complexity. That's where I think, and in all honesty, the average software engineering team out there has a mix of resources, some very smart people, some not so average developers, but at the end of the day, they all have to work together and maintain that code, right? So when you see even the smartest people dealing or struggling with the complexity, that's when you have to make them understand that it's not you, it's how your brain functions, and here's the science behind it, right? So making them understand that and acknowledge that the problem is not with them, the problem is with how the code is written, or how, and it's not just, the theory was actually founded in instructional design, right? It didn't come from software engineering. It was, the research were trying to find out how to better structure instructions in academic environments, right? So that is the important aspect, where making sure that engineers understand that it is not a problem with them, it's a problem of how our brain functions.
That makes sense. That's very important. It's important for the morale. It's important for various aspects.
Yeah.
And then when you try to solve this problem, how the cognitive load comes into that?
So that's where, the basic concept that our memory, and this is something that was mentioned in the keynote also, that our memory has a fixed capacity, right? 5 to 7 things at a point of time. So the example that was given was, sometimes we don't remember the drive to work, right? We might remember what was served at Thanksgiving last year, but we may not remember what we saw on the way driving to work. So our short-term memory is limited, right? So making sure that the code that is written is not taxing the reader's short-term memory, right? So that is when the problem is being solved. Now you've understood the problem. Now break the code down or simplify the code so that any unit of code does not have more than 5 things that the reader needs to focus on at any point of time, right? So, and then using tools like I mentioned, AI, for example, right, or CheckStyle or SonarCube or whatever your favorite static analysis tool is, to constantly keep that idea in mind that I have to restrict the number of things that my reader will have to pay attention to at 5, right? So that is the technique then to solve the problem, right? So understand that it's not you, it's your brain that is causing the problem, and then don't cause that problem for the next person who reads the code by fixing them.
This is great. Pranay, that was very interesting and also very, very useful. So now, folks, you know, your code should be as simple that even AI can understand it.
All right.
I love it. So thank you very much, Pranay, for coming. And for you all, remember, this is just the first interview. We will have tons of more absolutely amazing content that is going to stream live to you today and tomorrow and the day after. All of it will be streamed on TuxCare YouTube channel at Verbose Mode Podcast. So make sure you're following us there. With that, thank you very much.
Thank you very much.